Welcome back. In this lecture, I'm going to discuss about parametric curve and intersection between surfaces. So suppose that we have two surfaces. In those pictures, I have a cylinder, which is this one, and I have a sphere. Cylinder and sphere both have intersected on the red curve. So if we could visualize, you could see that this red curve, which lies on the sphere, also lies on the cylinder. In the picture on the right, you can see that the cylinder passed through the sphere. So now I have two curves. Here on this side, I have the red curve that is common to the cylinder and the sphere. On the other side, I have a similar red curve. So it depends on how you intersect two surfaces. Whenever two surfaces intersects, they meet definitely on a curve. Well, so here is a pair of curves, we'll say on a curve. So there could be, depending on the shape of the surface, there could be closed curve, open curve, or maybe more than one curve. So that's not that important. The most important part that we are going to discuss in today's lecture is how do we find the equation of such curves if we know the equation of the surfaces. And our strategy here will be that the equation of the surface, as we can see here, we have a surface, not the cylinder of the sphere, this is a different surface, z equal to square root of x square plus y square, which is a cone, upper half of a cone, and a cone shape is like an ice cream cone. And the other surface, z equals 1 plus y, so which is a plane. So in this case, a plane intersects on the cone, and then we want to find the curve of intersection. The sphere, equation of the sphere is given in Cartesian coordinate, and we want to find the curve in parametric form. So I'm going to assume today that you have listened to my other lectures about parametric curve. For example, consider the second example. Z equals 4x square plus y square, which is a surface. Y equals x square, which is another surface. We want to find the intersection between the two surfaces. I have a third example. Z equals x square minus y square, and x square plus y square equals 1. In all three cases, they are very similar. I'm going to work out how we find the parametric equation. Okay, parametric equation of the curve of intersection. Okay, so let's look at first example 1, and let's recall that the parametric equation. What is the form of the parametric equation? So the parametric equation will be expressed in terms of a position vector r, and the position vector will be expressed as a function of a parameter, and by default it is t. It does not have to be t. Any symbol can be used, and its first component x, position vector, which will be a function of t. Second component is a function of t, and third component is a function of t. Okay, so all we have to do is, by looking at these curves, we want to find some function of x, some function of y, some function of z that satisfies those equations. And since we want the intersection, maybe a good strategy would be to look at the intersection. If we look at the intersection, so then we can say z equals x square plus y square is one surface and equals 1 plus y the other surface. So we can set square root of x square plus y square equals 1 plus y, and that helps us. I can square both sides, and then we can simplify from both sides. I can see that y square common, that cancels out. So in this case I have this intersection, and which is still a curve, or that is the curve of the intersection in Cartesian coordinate, and that is easy to parameterize. So here the parameterization of free, so I can choose anything. So a simplest form would be x equals t. If I have x equals t, we can isolate y. So y will be half of x square minus 1. So half of t square minus 1. Okay, and then you can use one of the two equations, doesn't matter which one. So I'm going to use the one on the right. Z equals 1 plus y. So I can do a little bit of simplification. Well, first of all, I have to express this in terms of t. So that will be half of t square plus half plus 1 minus half. So going to be plus half taken out. Okay. Equals t, and we can just collect those terms together and write down each component of the position vector, and then we have just found the parametric equation of the curve. Okay, so that seems to be easy. Let's look at the second example. So the second example, the equations are, let me just copy down the equation for clarity. Okay. So you can approach the same way. So this time z equals 4x square plus y square. I can see that on the right side y equals x square. So I can bring it here. So I get x to the power 4, which was not needed, but then that helps now. Say, we can parameterize. We can represent. Start with one of them as a function of t. So we could start with z equals t. You can look at here. You can start with z equals t. Then you will be 4x square plus x to the power 4. So that will be difficult to isolate x equals what. But rather, if you start with x equals t, say x is represented exactly equal to the parameter t, then you can have z equals 4t square plus t4, and from the other equation y equals t square. So the parametric curve, which is the position vector, and t square 4t square plus t4, and this is the equation for the curve of intersection. So parametric equation of the curve of intersection. So basically this is just a freehand derivation. Is we are not going to follow any particular equation to solve the problems. Rather, we are looking at the concept. So and then we are working out in a way that what is our objective. So our objective is that I have uh, two surfaces given in Cartesian coordinate. In this case, the first one you can see z equals x square minus y square on the left, and the other surface is x square plus y square equals 1 on the right. And this time I am going to look at the solution intuitively. As I said, that there is no uh, definite procedure or formula. However, I have seen that first two examples, I looked at the two equations and put them together to make a single equation for the intersection. This one, perhaps I can do the same thing, but say what happens if I make them. Let's try to combine them together. So I can write here 1 equals x square plus y square, and then we can add them together. If I add them together, I get 1 plus z equals 2x square, or if I subtract, I will get 1 minus z equals 2y square, and so on. And 1 plus z equals to x square. Yes, you can start with x equal to t. You can say x equals t. Then you will have, say, z equals 2 t square minus 1. Well, then you can go back to the other equation and you can find x square plus y square equals 1. So you can solve for y, and then you have to have the square root, which is good, but it's not a problem. It's correct because parameterization is not unique. Every person can have their own form of parameterization. This time, I'm going to look at a slightly different way. I'm going to look at this equation, and in this equation I can see this is x square plus y square equals 1, and something nice I can say cos square t plus sin square t equals 1, which gives me x cos t, and for y sin t. So this is trigonometric function, and I can easily nicely, we like trigonometric function and it's useful for vector calculus than the square root function. And then now you look at the other equation, z equals x square minus y square. You can imagine what I'm going to get, cos square t minus sin square t. Well, this is the common trig identity, which equals cos 2t. So I have a parameterization r of t equals x is cos t sin t and cos 2t. You have definitely seen that this exercise here, the parameterization, you could come up with two formulation and maybe three formulation, and obviously two person will not come up with the same answer. The question is, which one is the best answer? There is nothing best answer. In real application, which is more appropriate for you would be which you want. Where do you apply that? what do you do next? So in many cases, if we come up with trigonometric functions, and for example, if we are dealing with integration and differentiation, then it's easy, integration and differentiation.